Okay, our next talk, I believe, is for a distinguished paper. This is a talk on fast and optimal extraction for sparse equality graphs, and the speaker will be Chun Lam.
Good afternoon, everyone. I'm Chun Lam from HKUST, and this talk will be about fast and optimal extraction for sparse equality graphs. So before diving into the technical details, we should first explain what is an E-graph. So basically, an E-graph is a graph plus some equivalence relation over the vertices. So consider the following expression, 2 divided by a times 2. The initial E-graph is basically just an expression graph. So as you can see, this is very similar to an AST, except that for the node 2, we somehow merge them together. So in a normal AST, you expect the node 2 to be duplicated, so you should have 2 copies. But for an E-graph, we merge those that are equivalents together so we can have a more compact representation. And for optimization purposes, people often apply rewriting rules to the equivalence graphs. So for example, in this case, we can rewrite the 2 multiplied by a into a left shift by 1 bit. And the dotted lines here represent that the 2 vertices inside are equivalent. So we have, so a times 2 is equivalent to a left shift by 1. So this is the basic idea of E-graph. And equality saturation workflow basically says that we apply those rewriting rules, which is what is called elaboration, until we can no longer find new results by applying those rewriting rules. So this is called saturation. And after this elaboration, we try to extract the optimal term that is the same as our target input term. And with this, we can get the optimal result with respect to the rewriting rules. And this framework is adopted by Cranelift, a JIT compiler for optimization, and there are also many applications using the recent egg library. However, there are 2 caveats with respect to this optimality result. So first, we need to elaborate until saturation. But this may not be feasible in some cases where the graph is large or the rewriting rules are very complicated. And in the second case, we must use optimal extraction in order to get the optimal results. And but this optimal extraction problem is actually very hard. Like NP hard to even approximate to a constant factor. So people usually just use heuristics or try to send the question to integer linear programming solver and hope that we can get the optimal results within certain timeouts. In our paper, our contribution is to propose the first fixed parameter tractable optimal extraction algorithm. So it does 2 things. So when the graph is sparse, we can get the optimal extraction in a relatively short amount of time. And the second thing is because we can have certain estimates of the sparsity of the graph, we can see if the graph is, if it is not sparse, we know definitely that our algorithm will not work quickly. But if the parameter is small, we know that it will definitely solve the problem really fast, and there's no need to guess the runtime of the algorithm. So before getting into the details, we first have to change the encoding of the E-graph a bit, because as a graph with equality relations, it is a bit hard to parameterize. So we formulate it as a bipartite graph. So we transform it into directed bipartite graph with E classes and E nodes. So the nodes here are the E nodes, which corresponds to the solid boxes here. And these circles are E classes. For each E class, it can point to multiple different E nodes. For example, this C3 points to the multiplication and the left shift operator. And this means that these 2 are the same, so they are in the same E class. And a set of vertices S is a valid extraction result if for every E node inside this S, we capture all its dependencies. And for every E class, we contain at least 1 member of it. So consider this the example on the left-hand side. If we extract these 3 vertices, this is not a valid extraction result, because for the left shift operator, we didn't extract these two E classes, even though two members of the E classes are extracted. And in the middle case, this is also invalid because for the E class C5, we didn't extract any of its member, which is A. And in the third case, even though there is no E class associated with the vertex 1, this is still considered valid extraction results according to our formulation. And the optimal extraction problem is to find some valid extraction results that contains the root E classes with the minimal cost. The root E classes means that you want to extract something that is equivalent to your input expression. And this problem is NP hard to even approximate. This can be shown by reduction from the set cover problem. So you can convert this set cover problem into an E-graph extraction problem with unit cost. And this is so this shows that E-graph extraction can be really hard. And when it is NP hard, you want to only solve it for some families of graph. And because we already have optimal extraction algorithm for trees, so if we don't consider the cost of sharing, we already have fast optimal extraction algorithms. So the natural choice is to use treewidth. So it measures the tree likeness of your graph. And in this case, the parameter treewidth, when it is small, it means that the graph is sparse. So treewidth is defined using tree decomposition. So consider this original graph. We can have the tree decomposition of that graph. A tree decomposition is basically a tree where each node maps to a set of vertices in the original graph. And this tree decomposition has to satisfy certain properties. For example, for every edge in the original graph, say this C1 points to the division operator, both endpoints must reside on some set in the tree decomposition. For example, this one. So both C1 and division are inside this node. And the second requirement is that for every vertex containing the vertex in the original graph, so for example, if we consider this C2, so these four nodes in the tree decomposition node contain C2, so they must form a connected component. And this is what makes tree decomposition powerful, because in the sense that we can have a cut property where we only have to consider things in the current spec. And to simplify things further, we consider a nice tree decomposition where we only have 4 kinds of different nodes instead of a general tree decomposition. But in a nice tree decomposition, the size is also linear to the size of the original graph. So we have, say, the empty node, where the set of vertices is empty. And we have this introduced node, where we introduce an additional vertex comparing to the child of the current node. And then we have forget. So we minus 1 vertex from the child. And at the end, we have join node, but we will not talk about here due to time limits. And our algorithm is actually very simple. We track valid partial solutions that are valid in the explored subgraph. So in our dynamic programming, we compute the set of valid partial solutions bottom up in the nice tree decomposition. So we start from B1 and then work our way up. And then for join nodes, we will somehow do subset convolution to join things together. This valid partial solution for E nodes, we must make sure that the solution contains all dependencies of that node. So this is quite similar to the valid extraction definition before. But for E classes, we do not require the solution to contain a member of that E class for now. So for example, if we consider the set of valid partial solutions for up to B4, so it means that we consider a subgraph containing 1 and C4. These 4 are all valid partial solutions. Even though for this solution containing only C4, we do not have the member, which is 1. But this is still considered valid for now. And then when we encounter an introduced node during our dynamic programming, we just copy all those valid partial solutions and add the introduced vertex to it. and then we try to remove those that are now invalid. So for example, starting from B4, we have these 4 valid partial solutions, and then we try to add the newly introduced left shift operator into each of the solutions. But some of them can be invalid, so we will remove them. For example, if we consider only a solution containing only the left shift operator, because C4 is also in the explored subgraph. So the solution containing only C4, only left shift is not valid. So it is not present in this set of valid partial solutions. And note that solutions can become invalid after introducing more vertices. So we cannot just check the newly introduced solutions. We have to check them all. And for forget nodes, we check that if we are now forgetting an E-class C, it must be satisfied now. So it means that we must contain its member if we want to extract that E-class. The idea is that in a valid tree decomposition, when we forget the E-class C, we know that we will not introduce its neighbors because all its neighbors should be added before. And so if it is not satisfied now, so if we don't have the member, we will never have, it will never be satisfied later. So we can just throw the solution away. And for the optimality and complexity, it seems that this partial solution set size grows exponentially because we are just always duplicating those solutions. But it turns out we don't have to track all of the valid partial solutions if our cost function is nice. So this requirement is monotonicity, and for things like positive cost summation cost, it is monotonic. So we don't have to track all the valid partial solutions. For example, for the set of partial solutions for B4, it turns out we only have to store 3 of them instead of 4 of them. And in general, the size is bounded by 3 to the treewidth, where the treewidth is the size of these bags, the maximal size. And this is much better than just having the 2 to the power of n, which is exponential. And typically, when we consider some small treewidth, for example, at most 10, this complexity is really good. So essentially, these terms are pretty small constants, and they are and the complexity becomes linear when the treewidth is small. So we implemented this in Cranelift for experiment. So we want to see if E-graphs in Cranelift have small treewidth, and because E-graphs in Cranelift are cyclic, we can apply our algorithm. And for benchmarks inside egg, so for the extraction gym, they require a cyclic extraction, which is a slightly harder problem. And we compared our results against the CBC ILP solver, and we also compared against Gyrobi, which is a commercial integer linear programming solver, to see if our algorithm is much faster than just trying to do ILP. And it turns out that in our benchmark, most of the E-graphs have treewidth at most 10. And if you only consider E-graphs that are a bit bigger, so they are less trivial, still 94% of them have treewidth at most 10. So this means that our assumption works for the Cranelift case. And in 96% of the instances where the treewidth is less than or equals to 10, our algorithm is significantly faster than integer linear programming solver. And it turns out the bottleneck of our algorithm is not really in our FPT algorithm, but it is in the heuristic to get the tree decomposition. So if we don't consider the part that computes the tree decomposition, because there can be many ways to do that, our algorithm is like 10 times faster than integer linear programming solver. So we have some possible future works. So because treewidth may be too big for some applications. For example, when we check the extraction gym for doing extraction with the egg library, we found that the treewidth can often be 40-something, which is a bit too big for this algorithm. So maybe there can be some alternative parameters. And also, a cyclic extraction is still unsolved. So we can actually generalize this algorithm to give us a still FPT algorithm for a cyclic extraction. But this requires double exponential on the treewidth, which is not very practical. And also, we would like to see if there are some heuristics that can be used to improve our performance. So for example, currently, tree decomposition libraries often try to get a much smaller treewidth. But it turns out in our algorithm, as long as the treewidth is, say, more than 10, you really don't need to optimize it further. So it's interesting to see if there are ways to get a faster tree decomposition or some other algorithms to do, say, fast subset convolution, because our runtime is actually dominated by the join nodes. So that's the end. I'm happy to take any questions.
Questions?
Hi. I wanted to ask if you have some results in cases where the cost function is less nice, you called it that.
Yeah.
And yeah, if you could explore for a bit, expand on that a bit. Thank you.
Yeah. So basically, the requirements of that nice cost function is that we have to make sure that the empty extraction result is cheaper than everything else. So if you extract something, it should be it should cost more than extracting nothing. And the second requirement is if you add some vertices and it is not present in the original two solutions, it should preserve that order. But that notion is a bit complicated, but we mentioned it in the paper, so maybe you can see if the formulation works.
Hi, thanks for the talk and congrats on the award. Can you, did you run this on any of the systems that use equality saturation, like end-to-end, to see if you're able to extract like an optimal program from one of the tools that have been built in the past years that use equality saturation?
Yeah, we actually only tested it with Cranelift because for benchmarks using egg, I think they often require getting that acyclic extraction, but that is much harder. And in Cranelift, we kind of avoided this problem because their E-graph are already acyclic.
Yeah.
So no.
Right. Okay, thanks.
Thank you very much for the talk. My question is sort of about, like you compared in the evaluation, your solver to like the ILP solver.
Yes.
But I'm actually curious to know sort of like how much more optimal are these optimal answers than sort of the quick and dirty ones? For example, if you had an extractor that was just going by like assuming tree width of 1, so this is the optimal like tree extractor, assuming that the answer is going to be a tree, how much worse do the results degrade if you have like a tree width of 10?
Yeah, I think we just implemented something with Cranelift where we found the size. So we were trying to like minimize the size of the final code, and I think we got like 2 to 3%, which is not a lot. But there's also another problem with the architecture of Cranelift. So they are so in their code they are kind of assuming there's no sharing. So they implicitly assume that because they try to compute the optimal extraction cost for every single E classes. And in that sense, you can't have any sharing because they sum them up later. So there's some improvement, but we expect like a bit more improvement if that thing is fixed.
Thank you.
Okay, let's thank the speaker again.